จ้าครับอันนี้คืออ่านหน้าจอหรือยังครับผมไม่ได้ยินเสียงไม่หรอก
ได้ยินไหมครับทีนี้
ได้ยินแล้วครับอันนี้ผมส่งชื่อไปแล้วอันนี้คืออ่านหน้าจอแล้วป่ะครับ
อัดแล้วครับอัดแล้วครับ
โอเค
เชิญ
ครับผม
ไม่มีปัญหาเลยครับพิมพ์
ได้
มา
ครับ
ได้เลยครับ
โอเคครับ
โอ้ยโอ้ยมีเสียงกล่องโอเคครับyeah oh yes this one next thing PP we cannot save we cannot transfer okayมีมาพิมพ์มานะครับตอนนี้4 คนนะครับมีณภัทรนะครับผมพูดด้วยเผื่ออัดแล้วจะได้ไม่ลืมครับณภัทรมีธนนัทนะครับโน
อาจารย์ไลฟ์ทาง YouTube ยังครับเดี๋ยวผมย้ายไป
ไลฟ์แล้วครับเชิญเลยครับ
โอเคครับ
YouTube มาแล้วมีประภาวิทย์มีกสิดิษฐ์มีปัญ
โอเคงั้นผมย้ายไปเลยนะครับอาจารย์
ตามสบายเลยครับthis this one มีคนมาด้วยตัวที่เป็นสักข้อนะครับเขาก็บอกเอาเลยนะช่วงเวลาที่จะสอบปลายภาคคุณมาแล้วบอกช่วงเวลาการเก็บคะแนนอะไรอย่างนี้ด้วยมาเรื่อยๆก็ออกมาอีกครับtoday is 24 th it's 12:40 to 15:20 I will just copy and read here okay now started yesก็so good afternoon everybody welcome you to SCI 33205 M604, right? 3205 M604, which is physics number 4, right? เลื่อนหน้าช้า Okay, we are here at the we are here at the topic of Lenz's law, right? In order to find the direction of the induced electromotive force, right? Right there in yeah. If you have the permanent magnets like this here, okay, and if you want if you want to see some effects from this one, right? Good note. If you want to see some effect, how the current will appear in this copper conductor, right? The circular loop. If you have N pole, right? This is the north pole of the permanent magnet. And you point the north pole to the circular loop of the conductor, and you put it, okay, you move it into the face of the circular loop, right? And you would find that there will be magnetic flux difference, right? Before that, the conductor can realize only a little amount of the magnetic flux, right? Which is at T1, right? 5B1, and when you move it to be closer to the conductor will realize, okay, will perceive or will feel that the magnetic field is stronger. Okay, that's why they say the longer vector. And with these two states, with the comparison of both situations, we find that there will be change in magnetic flux, okay, which is denoted by delta phi b. Okay, delta phi b is something important to this scenario, all right, because the EMF will emerge due to the quantity of flux change. Yeah, or there is a flux change in this direction, and Lenz found that there will be the conductor doesn't like that situation. Okay, he tries to keep the amount of the magnetic flux, okay, to be the same as the first situation, which is the 5B1. So in order to do that, okay, you just measure the length. Okay, the conductor will measure the length of this vector, the flux chain, and he make the same amounts of flux chain to make the magnetic flux. Okay, and then the direction of the induced magnetic field is opposite to the chain in flux or flux chain. Okay, this is B induced, and that's what happened. And in order to get B induced, okay, the conductor should behave itself, okay, by generating a current, okay, rotating in this circular conductor, and yeah, the direction here should follow the right hand rule. Okay, you
ไอ้
leave
เหี้ย
your
เอ้ยแล้วกูก็เรียนชัดเบอร์บอลต่อไม่ได้เพราะว่าแม่งคือสอนเรื่องฟาราเดย์ลอซึ่งเป็นเรื่องที่กูต้องเรียนไอ้เหี้ย
มีเปิดไมค์ด้วยนะครับ the thumb direction points same as the direction of the B induced, okay, and your remaining four fingers will represent the direction of the current rotating in this circular loop, okay, and that's the first situation. Okay, it's straightforward. You just move the north pole to the circular conductor, but in the opposite way. If you move the south pole, okay, on the other hand, if you move the south pole into the conductor, what is going on? Okay, let's make an analysis in the following. You move the south pole, right? In but from what we have heard at the beginning of this chapter, the north pole is the place that generates the magnetic field lines, right? But the south pole is the place where the permanent magnet receive, right, or get the magnetic field lines. So you can see all the arrows of the magnetic field lines pointing to the south pole of that permanent magnet. Okay, and yeah, of course, the conductor is the main object for us, right? It's the main interest for us. He realized that there is magnetic field lines in this direction, okay, in the upward direction, in the vertical direction, like this, okay, in the up direction. And when you move it, when you move the permanent magnet to be closer to the circular conductor, you will find that at the state one, okay, the flux vector phi b1 is has the height like this, okay, is of the height like this. And when you move it closer, this vector is going to be stronger, which means it has a longer magnitude, okay, which is phi b2. And you could find the difference between these two states, right? Two states. And yeah, it's called again the flux change, okay, delta phi b. Yeah, but the conductor is the lazy guy, okay? He's a lazy person. He doesn't like this behavior when someone change the environment around him. So he tried to compensate the additional vector of the flux in this direction, okay, by making himself, okay, the magnetic field, okay, in the opposite direction, but with the same magnitude, with the same length of this vector. มีใครเข้ามาอีกไหมครับไม่มีแล้วนะโอเคผมพะวงเดี๋ยวผมลืมไม่กดรับคุณนะครับโอเคสุภสินที่พันมาครับขออนุญาตแคปเจอร์ที่ YouTube ไว้หน่อยครับyeah, the induced magnetic flux is gonna point in the opposite way again, okay. This one again is pointing in the opposite way, okay, to the flux change vector. And here again, but the flux change vector is pointing upward, okay, which is opposite to this situation on the left side. The B induced will follow the same, okay. It will have the opposite direction to the flux change vector, okay. Now it's going to point downward, and yeah, in order to get the B induced, the magnetic field the induced magnetic field pointing downward like this, you have to lay down your right hand, okay, your thumb direction along the direction of the induced magnetic flux or vector B, and you will find that your remaining forefinger is gonna represent the current that should flow in this circular conductor, okay. And yeah, your four fingers would give the would give the direction of the current flowing in the circular conductor like this, okay. That's the conventional from the right hand rule, okay. That's the first situation. You move both permanent magnets, whether it's with the head of north pole, with the head of south pole toward, okay, the circular conductor. But let's consider the different situation if you move it out of the circular conductor. For example, okay, let's consider first the conventional way we leave the North Pole toward the conductor, but now we don't move it to จริงๆ605จะเข้ามาเรียนพร้อมกันเลยก็ได้นะแต่ว่าเอาไม่เป็นไรเอาตามตารางเดิมก็ได้นะครับเดี๋ยวจะหาว่าผมขี้เกียจสอนรอดเดียวif you let's consider the conventional way first. Okay, the North Pole pointing to the circular conductor, but now we don't move it toward the conductor. We move it out of the conductor, and we would find that before the flux has the vector, okay, pointing downward, right? And when you move it out of the conductor, the magnetic flux is going to be lighter, right? It's going to have less impact to the conductor, right? Here, at the first state, you have 5B1, okay, magnetic flux with quite long, okay, long vector, and after that, you move it out of, okay, the conductor, and you get lighter amounts, okay, or smaller amounts of the magnetic field or magnetic flux, okay, that's represented by the shorter vector here, 5B2. We make the difference in physics, right? The final state minus the initial state, right? So we get the delta phi B, which is the difference of the flux change or the difference of flux, okay, between those situations, and we find that the flux change, okay, vector is pointing upward like this, okay, it has lighter amount of magnetic field, right? So the flux change is pointing upward like this, and the conductor is the lazy person, okay, he doesn't like that situation when someone disturb him. He tried to compensate or to remove or get rid of this flux change, so he has to generate by himself the magnetic field, okay, in the opposite direction to this one again, okay, this is upward, so he generates the magnetic flux in the downward direction, okay, with the same length, okay, the same magnitude as the flux change. But now let's consider if he wants to generate the induced magnetic flux with the downward direction like this, okay, he has to use his right hand, okay, and this is the thumb direction. His remaining forefinger is gonna give us the direction like this, okay, and that's the first case, the third case, okay, when we move the North Pole out of the conductor. Now let's consider the situation when we move the South Pole of the permanent magnets out of the conductor, okay. Before that, we get quite strong magnetic field lines with the upward direction, and when we move the permanent magnets out of this conductor, we're gonna get lighter magnetic field, right? Or the smaller amount of magnetic field lines. So at state 1, we get the strong, okay, flux, which is 5B1, and at the second stage, second situation, we move the permanent magnet out of the conductor, we get lighter magnetic flux, which is 5B2. Okay, that's why we can see here the shorter vector. And in physics, we have to measure the difference, right? The final state minus the initial state, okay, 5B2 minus 5B1. We can observe that there is reduction of the magnetic flux, so we get delta 5B, okay, vector, and its direction is downward, right, like this. In the conductor doesn't like this situation again. He tried to create or compensate the additional shape, the additional magnetic flux. Okay, here we have the downward magnetic field, so he has to generate the upward magnetic field, and he laid out again his time direction in the same way as the magnetic flux that has to be induced. Okay, and yeah, his 4 fingers will represent the current that will happen in this circular. Okay, and that's all. Those are all 4 cases that we can use and we can observe. Okay, whether it's moving into the it's moving toward the conductor, is moving out of the conductor. That's matter, and that's those 4 figure or situation are taken from one book, and here is another situation. If we take it, if we consider it from another book, right? Here we have the currents flowing upward like this, and from the Ampere law or the right Ampere just use the right-hand rule, right? So the induced, it's quite related to the Biot-Savart. Okay, if you want to find the strength of the induced magnetic field, you just use your right hand, your thumb direction, laying down according to the direction of the current. Your remaining 4 fingers will represent the magnetic field, right? Magnetic field lines, which has the circular shape like this. And yeah, because this conductor does like, okay, he has to before that, if we don't let the current flow, okay, there will be no magnetic field, the green one here, okay, magnetic field lies the green one. But when we let the current flow upwards, as in the okay, if we let the current flow upwards, okay, according to the figure, okay, as in this figure, we get the magnetic field lines like this, and this is the conductor, another conductor, which is around, has a closest loop, right? Whether it's rectangle or circle, okay, whether it has a rectangular shape or a circular shape, okay, doesn't matter. The important thing is that we have the closest loop of the conductor. Yeah, and that's what we could expect. Yeah, that's what we could expect again. Okay, even it's different situation. We don't have permanent magnet, but we just use the principle of the induced current. Okay, this conductor doesn't like the situation when someone disturb him, okay, by putting the magnetic field into his internal area here, okay, his area. So he tried to compensate or to get rid of the additional magnetic field by generating the magnetic field with the same amount, but in this opposite direction. You can see here, this is the generated magnetic field. And in order to have the magnetic field to compensate or get rid of someone disturbing him, he has to make the current, okay, and he has to generate the current, and the current direction should follow or satisfy this magnetic field. Okay, again, you use the right hand, and your forefinger will represent the magnetic field lies here. Okay, the induced one, and your thumb direction is gonna give you direction of the induced current. Okay, here is the Lenz's law. Okay, it's quite close to the Faraday's law. Faraday's law will give you the quantity, okay, how much you could get the electromagnetic force, okay, which is simply known as voltage. All right, here, we have another type, okay, which is quite related to the former four figures, four previous cases. We have again permanent magnets and the circular coil, and we move the permanent magnets. Okay, that's a conventional way, right? The south pole of the permanent magnet or any magnet will be the place where magnetic field line is gonna get into, right? And at the north pole side, we have the place. We have the source, right? The source that generates or let the magnetic field lines get out of. Okay, yeah, getting out of, and we move these permanent magnets toward the currents to the circular coil. And of course, this guy, the conductor, that's like that moment, okay, when someone tries to disturb him, okay, he tries to act against this increased amount of the magnetic field, okay, in order to get rid of the additional amounts of the magnetic field, he has to generate the magnetic field in the opposite way, okay, and in order to get the magnetic field in the opposite way, he has to use the right hand, okay, your thumb direction pointing into the magnetic permanent magnets, and your four fingers will represent the induced current, and then you get the current flowing, turning around like this. All right, and yeah, here is the figure that explains how or the mechanism of generating the magnetic field to be against the additional the increasing amount of magnetic field stemming from the movement of the permanent magnets. Here, in order to have the magnetic field like this, okay, from right to left, we lay down our thumb, okay, according to the direction of the magnetic field. We have the four fingers, which represents the direction of the induced currents, the I vector here. All right, yeah, you can see that this is the place we can consider as the North Pole. Okay, North Pole is the place that generates the magnetic field lines, right? And we can see on the right side that here we have the South Pole, okay, because this is the place where the magnetic field lines are getting into, okay. Yeah, something else, you can have, again, the same situation, even you don't use the permanent magnets. If you use something different, but it has the same property, it's called electromagnet, okay, it's not permanent magnet. Both are magnets, okay, the object that generate the magnetic field, but permanent magnet has nothing to do with modification. It just simply deliver the magnetic flux, okay, without any modification, without any efforts. But electromagnet is the object that can generate the magnetic flux in the same way as the permanent magnet, but we can control the generation of the magnetic flux, okay, by turning on, switch on the currents, okay, or switch off, okay. If you let the current flow like this, okay, and yeah, you will find that the magnetic field is gonna point into this direction, right? If you use your right hand and your forefinger represents the current movement, okay, which is the direction turning around like this, and your thumb direction is gonna be the direction of the magnetic flux, okay, which points to the left right? Okay. And when you didn't switch it, nothing happened. The coil realized that there is no magnetic flux at all across my surface. But when you switch or turn the switch off, okay, now there is current movement, and the magnetic field will start to flow or go in this direction. And the conductor will realize that someone disturbed me. Okay, he let the magnetic field passing through my area like this, from right to left. He doesn't like that situation. He tried to get rid of the increasing amount of the magnetic field. Okay, before that, at the first stage, he doesn't have magnetic field light all across his surface. But in the second situation, someone disturbed him. Okay, in order to get rid of the increasing amount of magnetic field, he has to generate the magnetic flux in the opposite way. Okay, in the opposite way to the direction of someone putting or placing the magnetic field in him. Okay, so the direction that acts against this one, okay, should be the one that are directed from left to right. Okay, from left to right, that's the decided direction for the magnetic field that this conductor, I don't know, it's green or no, it's orange or I don't know. This conductor should generate the current in order to have the magnetic field from left to right sides, and here he generate the current. Okay, the time direction represent the magnetic field which points from left to right, and the remaining 4 fingers will represent the induced current, which is this one. Okay, I hope that you completely understand. Okay, now we will solve. We will have an example to our situation regarding the Lenz's law and so on. Here we 20 นาที14ผมต้องปล่อยคุณใช่ไหมครับโอเคนะ20 นาทีชวินมาครับโอเค all right, here this is taken from the book number 1, example 21.2 figures 78. This is a special device, okay, or special apparatus in the laboratory. We have permanent magnets, okay, the North Pole, the South Pole, and of course the North Pole will generate is the place where the magnetic field line start, right, and it's gonna end or reach the South Pole, okay, and assume that all of magnetic field lines are pointing straight. Okay, there is no curvy movement. Okay, only straight line direction for the magnetic field lines. Okay, and this is the spatial device. He has also the owner of this figure has also the conductor, right? The copper wire, which has circular shape. Okay, approximately circular shape, and at the end of the circular conductor is we connect the voltmeter, I don't know, voltmeter or ammeter to this conductor, right? And they say the area, the cross-sectional area of this conductor loop, whether it's ellipse, whether it's circle or any kind of shape, okay, of the conductor, but let's say it has the area of 120 square centimeter, or if we convert it to the square meter, it's going to be this number divided by 10,000, right? So it's going to remain 0.012 square meter. And this conductor is not perfect, okay? It's not superconductor, which operates in very, very negative temperature, okay? It has its own internal resistance, okay, because it's not perfect metal, and assume that from one side to another end we have 5 ohm for the resistance of this conductor. And now let's take a look at the question in this one. Yeah, that device has a uniform magnetic, okay, it's uniform across all the area in that device. Okay, the amount, the density of magnetic field lines here are considered or assumed to be the same. Okay, there is no place where the magnetic flux is denser than the other area. Okay, everywhere here has the same density for the magnetic field line, and assume that if someone can control this permanent magnet, the permanent magnet, the magnetic field changes. They don't say from what value to what value, right? So they just say that there is a change of the magnetic flux per time as 0.02 Tesla per second. Okay, in 1 second, the magnetic field line is higher by 0.02 Tesla. Okay, in 1 second. And what else? The area cross-sectional area 120 square meter. Okay, the internal resistance of that conductor is 5 ohm. Okay, find the magnitude of the induced EMF and the induced currents in the circuit. So we have to talk about the Faraday's law, right? We have Faraday's law as this one, right? And yeah, it's epsilon is band, right? Band omega, right? Band omega is that's the for the generator. This is Faraday loss is minus n and delta phi b by delta t, right? And phi b is this one. Okay, if you want to see the expression of phi b from the beginning of this chapter, be a cos phi, right? Yeah, phi is the angle between the normal vector of that conductor to the magnetic field direction, right? Vector B and vector A. Okay, dot product between vector B and vector A. Okay, that's why we get cosine. Yeah, we are gonna use that formula in order to solve this one, right? So let's start to do that. It's better to use this one. Okay. All right. How to do that? They asked us about the magnitude of the induced EMF, right? So we have to consider the formula by Faraday, okay, which is epsilon equals minus n and delta phi, right, by delta t, right, right there. Okay, this formula delta phi by delta t. All right, and but they didn't ask us about the actual value for the induced EMF, but rather they asked us the magnitude of the induced, okay, magnitude. So we should take the absolute value to this expression. So we're gonna have the absolute of epsilon is equal to absolute of minus n, right? In delta phi divided by delta t and the absolute value like this, right? In yeah, the absolute value will be distributed to both quantity, right? So it's gonna be this one, right? The absolute value of that one and the absolute value of delta phi b actually. Okay, phi b. divided by delta t right here. Yeah. Yeah, this one, we will remove the negative sign, okay, because it doesn't satisfy the absolute value, okay. So we take only the positive value for that. So it's going to be n and the absolute value of delta phi b, right? So he said that there is flux change, but it's not possible. This is delta b per time, right? So we have to consider the delta phi b, but phi b is b a cosine phi, right? Phi is the angle between the normal vector of that area to the magnetic flux direction, right? So delta phi b is, in this case, we would see that in this one, the area doesn't change with time, right? Because we didn't increase the size of the conductor at all. And there is no rotation of this conductor, so the phi will be the same, right? So there is no change in angle. And you can see that here the direction, right? This is the normal vector, and the green one is the normal vector for the area of this conductor. The blue one is the magnetic field direction, right? The b vector and the n vector. So the angle between these two vectors is 0 degree, right? So we can substitute 0 to this one, and cosine of 0 is going to be 1, right? And b change with time, but the area doesn't change. So we would have delta phi b is going to be a times delta b, right? Okay, delta phi b will be a delta b. So we will substitute it into this one. All right, a and delta b, right, in divided by delta t, right? And yeah, because the area will never be negative, okay? Have you ever heard any area to be negative? Okay, usually the area is positive. We can move it out of the absolute symbol. So we would have right now n and a, right? And what we get here is delta b by delta t. And the question in this example says that delta b and delta t is 0.02 Tesla. So we will substitute. Okay, from the figure, even they didn't say how many turns of the coil, you can see here that there is only a single turn for the coil, right? So it's going to be a single turn, okay? N number 1, n is equal to number 1, okay? One turn. And A is the area of this conductor. Okay, we don't know whether it's circle or rectangle. Okay, they didn't say the detail. So we will substitute the 0.012 to the variable A, 0.012, and square meter, and delta B by delta T is what they have already provided here, which is 0.02. Okay, you can also leave the absolute value, but it doesn't matter at all. Okay, 0.02 Tesla per second. Tesla per second, right? And closing. Okay, like this, and yeah, we leave it. We move. We place all these three amounts into the calculator. Okay, we get the multiplication result. Okay, what is that? รายการอะไร12 2 ใช่ไหม12 2 24 okay 24 right in 24 it's equal to 0.00024 right so 5 position the 5th position after the decimal point and we get that in the unit for the epsilon is the volts, right? And if you want to represent it better in the better way, we would say 24 times 10 to negative 5, okay? Or yeah, volts. I hope it's correct. I'm not sure about that. 24 times 10 to 5. Yeah, here, okay? Or you say it in milli, right? Milli would be there, okay? So it's going to be 0.24 millivolts. All right. Yeah, the next quantity that they would like to know is the induced current. So it's not difficult at all. So we just remind ourselves the Ohm's law, right? George Georg Ohm, okay? Ohm's law, V/I/R, right? If you want to find R, okay, epsilon is equivalent to V. So we would formulate this figure, this formula as V by R, right? V by R, and V is that thing, okay, which is 0.24, right? Oh no, stupid. Use the SI1, 24 times 10 is to negative 5 volts. All right, and R is the resistance that this conductor has, okay, right, which is 5 ohm, okay, leave it 5 ohm. All right, and yeah, we would find that it's going to be 4.8, right, times 10 is to negative 5, but it's ohm, okay, it's not volts. We need for resistance. Oh no, I'm stupid. It's ampere. My God, it's ampere, right? In if you want to say it in micro scale, for example, micro, you would have 48, right? 48 micro ampere, okay, very tiny amounts of current. 48 micro ampere, and that's it. I hope it's correct. นะครับไม่พานี่จริงด้วยนะครับไม่พาคุณเสียหน้านะ yeah, we have finished the first example, and let's consider the second example. There are three cases. The first one is อันนี้มาจากหนังสือคนละเล่มนะครับis taken from a different book, right? The book number 1, this one, okay, the former problem, but right here we take the example from the book number 2, okay, example 20.2. A coin with 25 turns of right, okay, is wrapped on a frame, okay. You cannot count, okay, the number of turns in the coin by eyes, okay, in the figure. You cannot say 1, 2, 3, 4, 5, 6, 7, 8, 9 or something like that, because they simply say here there are 25 turns, okay, in the Y in the coin, and with square cross sectional 1.8 centimeter. ผมลืมบอกไปว่าการบ้านที่คุณทำมานะครับธนพัฒน์ยานโอเคกันนะผมต้องชี้แจงคุณนะเวลาเขาบอกว่า square on a side of นะครับภาษาอังกฤษที่เขาบอกว่าสี่เหลี่ยมแล้วก็มีด้านหนึ่งขนาดเท่านี้เวลาคุณคิดพื้นที่นะครับคุณต้องเอาค่านั้นมายกกำลังสองนะ คุณไม่ใช่เอาค่านั้นไปคูณเฉยๆนะครับซึ่งคุณทำมามันก็ไม่เยอะเนาะแล้วแต่ห้องด้วยนะทำผิดทั้ง2ห้องนะครับทั้ง604ทั้ง605นะครับเวลาเขาบอกว่า square with a side of หรือว่า on a side of หรือยังไงเนี่ยบอกว่าด้านเป็นเท่าไหร่คุณต้องเอาค่านั้นยกกำลังสองนะเพราะว่าพื้นที่ของรูปสี่เหลี่ยมจัตุรัสมันคือด้านยกกำลังสองนะครับโอเคไหมไม่ใช่เอาค่านั้นเราไปวางเป็นสแควร์เมตรนะครับมันก็ผิดแล้วโอเคไหมมันต้องเอาด้านมายกกำลังสองนะครับตรงนี้ยกเว้นแต่ว่าโจทย์คุณอ่านดีๆนะไม่ใช่ลอกกันบ้านเพื่อนนะคุณยกเว้นแต่โจทย์เขาบอกว่ามันมีพื้นที่เท่านั้นเท่านี้เลยอันนั้นคุณไม่ต้องยกกำลังนะครับโอเคไหมสี่เหลี่ยมจัตุรัสมีพื้นที่เท่านั้นนี้คุณไม่ต้องยกกำลังแต่ถ้าเขาบอกว่ามันมีด้านหนึ่งเท่าไหร่คุณต้องเอาเลขนั้นมายกกำลังนะครับโอเคไหมครับผมตรวจแล้วผมเจ็บปวดโอเคไหมผมก็ไม่อยากตัดคะแนนคุณแต่ว่ามันก็ผิดหลักการโอเคไหมครับwith a square cross section 1.8 centimeter on a side เนี่ยครับโอเคไหมอย่างโจทย์ข้อนี้คือชัดเจนเลยกรณีของคุณเขาบอกว่าเป็นสแควร์สี่เหลี่ยมจัตุรัสแล้วก็ 1.8 เซนนะครับบนแต่ละด้านหมายความว่า it means that you draw it like this okay here you use the ruler and you would see that it is 1.8 centimeter all right so you cannot simply say the area of this square is 1.8 square centimeter okay this is the basic knowledge from the primary school a square is 1.8 cm okay the square 18ได้เท่าไหร่256ป่ะจำไม่ได้1.8 and 1.8 what is that มีใครเท่าไหร่ช่วยผมด้วยผมก็เซอร์เบลออายุเยอะแล้วนะครับมันไม่สดชื่นเหมือนตอนน้อยๆนะพึ่งเครื่องคิดเลขอย่างเดียวนะครับทุกวันนี้where is that 18 หายไปไหนแล้วเครื่องคิดเลขไปไหนแล้วเดินเลยGoogle ก็ได้ครับเคยไหม Google ก็ได้18 and 18 right 18 times 18ดันไม่เป็นสูตรปุ๋ยครับ R324 yes it's 3.24 ไปลง6เลยนะsquare centimeter okay, and that's the unit for the square yeah, okay you get 3.24 square centimeter and if you want to convert it to square meter you have divided the whole amount by 10,000 right 10,000 yeah yeah the uniform magnetic field happens passing through this coil and with the 25 turns we have 0.35 ohms okay of resistance of the whole length of this conductor in what else the magnetic field is perpendicular to the plane right of this coil it means it has 0 degree to the normal vector of this plane right if the field change from 0 Tesla to 0.5 Tesla in 0.8 seconds what is the induced EMF in the coil when the field is changing okay all right no problem okay let's do first the first question let's solve first the first question epsilon is minus n right in delta phi b by delta t อันนี้จะสูตรค่อนข้างยุ่งยากนะครับขึ้นทีแรกเลยอาจจะแทนไม่ได้นะครับต้องไล่ไปว่าโจทย์เขาให้ตัวแปรอะไรมานะครับต้องไปดูไฟ b ว่ามันอันไหนเปลี่ยนนะครับ alright we have to know which variable is going to change in the expression of phi b, okay, phi b or phi bt, okay, actually it can change with time, right? Is b that can change with time times a that can also change with time times cosine, right? It's cosine phi. Oh no, small phi, and the phi, the angle can also change with time if we talk about the generator, okay, because there is rotation. Because there is rotation, the angle can also change with time. So we leave the functional dependence of t, okay, to all three variables, and we consider what they provide. Okay, there is no change of the area at all. Okay, the size of the conjugate is the same. So a t doesn't depend on time. Simply say a. Okay, and the phi. Phi is the angle between the normal vector of this one to the magnetic field, which is 0 all the time, right? So this conductor doesn't rotate, doesn't move at all. The angle phi t will not depend on time. It's going to be phi, okay? And in this case, you have the plane like this, right? In this is the normal vector, and the b vector is this one, right? B vector like this. So the angle between n and b, okay, it lies in the same direction. So direction between angle between vector n and vector b, okay, the angle,นะครับใส่หมวกให้นะครับ the angle between vector n and vector b is 0 degree, right? So when phi t is all the time 0, so this one is going to remain number 1, right? We don't have to write it at all. bt changes with time, right? The magnetic flux changes with time from 0 to 5 Tesla per 0.8. So let's continue our derivation. What quantity they want to know? Induced EMF, okay? Please pay attention to this word because it's not magnitude, so we don't have to leave the absolute value on both sides anymore, okay? Because they just ask the plain value without any magnitude, okay? Without any absolute operator. So epsilon right now is going to be minus n, and of course, let's summarize this. Phi bt will be a and b, only b, okay? Magnetic field that depends on time. All right, and we will move this one, okay? We will simply substitute this one into this expression, okay? B final, phi final minus phi initial, right? That's the natural way in physics observation of two situations, right? Yeah, the final situation is going to be the second one, right? But they don't say it. They just say a and delta b, right? A and delta b divided by delta t, right? And yeah, we still have minus n, right? Minus n. How many turns are there in this one? They say 25 turns. Okay, no problem. We leave it 25 turns. Okay, 25 turns. Okay, that's the value for variable n, and we don't need to, we should not forget the negative sign at all. And let's consider a. A is the cross-sectional area, right? Which is here what we have got 3 to 4, right? Is 3.24, but it should be in SI unit 10 raised to negative 4 square meter. All right, and delta b, okay, if we write down minus a in delta B, delta T, right? So the next one is delta B by delta T, right? So the initial state, which is B2 minus B1, right? So it's going to be B2 is 0.5 Tesla, 0.5 Tesla minus 0 Tesla divided by time. How long did we observe? 0.8 second. 0.8 second, okay. It's not so far. Like this, okay. We leave it into the calculator. And เดี๋ยวผมขอคิดเลขข้างนอกนะครับที่เกียจสับจอไปมาครับเดี๋ยวคุณลายตาแล้วไปไหนแล้วอ่ะอ๋ออยู่ตรงนี้โอ้ไม่ก็ right นี้เราอยู่ที่หน้านะครับประมาณ 1.6 โอเคโอเคOkay. We have to substitute everything, right? After the calculation, you get what is that? What is the value for that? Minus เดี๋ยวผมคิดให้ดูคุณดูดีกว่าจะได้ชัดเจนตรงไปตรงมาเดี๋ยวหาว่ามั่ว What is that? Minus, right? 25 times 3.24 times 1 3.4 e times คุณจะเห็นชัดๆtimes 10 raised to negative 4, right? Minus 4 and times 0.5 divided by 0.8 second, right? And yeah, that's it. And generate. It's 50. Oh my god. 00500625. What is that? Here it's going to be minus 0.005 to 50 602 6025 506 625 625. Okay, and that's the volts, right? Okay, we get the negative value for the voltage because this is the negative just represent the opposite direction, okay, for the induced magnetic flux, right? That's typical thing from the Lenz's law, and yeah, we get epsilon for that. Let's check 0.05. นี่นะครับตรงเป๊ะนะครับโอเคไหมครับ or if you want to say it in millivolt scale, it's in millivolt scale. Oh, it's not approximation at all. Okay, I'm gonna bring you to the wrong thing. It's not approximation. If you want to say it in milli scale, okay, minus 5.0625 and millivolts, like that. Okay, that's for the first quantity. The second quantity is the direction, right? Direction. What do you think then? In order to get the current movements, this one, the direction. Okay, direction of the current or induced EMF direction should be, because there is magnetic flux change. okay, in this area. So delta phi B is going to be this direction, right? So delta phi B. So but we have to the conductor doesn't like, okay, the change in its cross-sectional area, right? So he has to generate the magnetic be induced in this way, right? Be induced in this direction, right? And yeah, we should have the be induced. We use just different. Okay, be induced in this direction, right? And of course, we will apply the right hand, okay, to get the current direction, and you lay down your thumb direction pointing downward, you get the remaining four finger direction like this, right? See yeah, the current is gonna move in this direction, okay, and yeah, that's the current. Okay, it's gonna move like this. If we apply the if we apply the right hand, right? The right hand to this one, your remaining four finger will give you the direction of the current in this way, right? Yeah, that's it for the question about direction, right? And now let's go on to the induced current. Oh, it's not difficult because we know that the resistor of this one is 0.35, right? So we will divide that one. Okay, I will be absolute value of EMF divided by R, right? Which is VIR actually. So we have 5.0625 millivolts, or you say volt as well, right? Divided by 0.325 ohm, right? That's it. 325 ohm. Oh, 35, not 325. I'm stupid. 35 like this, okay, and you leave it into the calculator again. 35 divide again 5. Okay, also 5 done generate. It's 014464. 014464. It's equal to 14464, and the unit for that is ampere, right? That's the amount. And the unit for the current, right? 0144. Let's check. Yeah, it's correct here, right? 0144. If you say it in milli scale, it's gonna be milli, right? 14.464, right? Milliampere. Okay, both are correct if you want, but the last one would be more appropriate. We still have 10 minutes remaining. Okay, let's take a look at this one. Circular coil. ผมขออนุญาตเข้าห้องน้ำแป๊บนึงครับขออนุญาตปัสสาวะแป๊บนึงครับ 8 นาทีครับ okay a circular coil of wire okay with 500 turns and average radius of 4 centimeter is placed 60 angle to the uniform magnetic field between the poles of a large electromagnet. Okay, it's not permanent magnet. It doesn't matter whether it's permanent magnet or electromagnet. Okay, and the field changes from doesn't say the value from what value to another value. The changes at the rate of this value. Okay, it decreases. It's decreasing. And what is the magnitude? Magnitude of the resulting induced EMF, right? So let's open a new page in order to solve this one. Yeah, I don't know from which book, first book, but yeah, we start from the same formula, minus n and delta phi b divided by delta t, right? And we'll go ahead with that phi b t is b t a t cosine phi, which depends on t, and we will see which one that's it doesn't rotate, so phi doesn't change. The loop or the conductor doesn't change its area, so AT is the same. Magnetic field is only the variable that changes. Here they say BT changes like this. Okay, so phi t, oh no, small t. Okay, phi t remains constant, so it's only 5, and it's equal to, what is that? What is the value for this one? You cannot simply take 60 angle ผมย้ำอีกรอบนะครับเดี๋ยวคำทดสอบมีคนผิดนะอย่าเอาค่านี้ไปใส่ในไฟเลยนะครับในไฟในฟีนะครับหรือว่าเซต้าแล้วนะเพราะว่ามันเป็นมุมระหว่างเวกเตอร์ b กับระนาบหน้าของขดลวดนะครับไม่ใช่นะไฟนี้เป็นเวกเตอร์เป็นมุมระหว่างเวกเตอร์ normal ของพื้นหน้านะครับเวกเตอร์ที่ตั้งฉากกับหน้าขดลวดนะครับโอเคไหมห้ามเอามุมระหว่างหน้าขดลวดกับสนามแม่เหล็กไปแทน60เลยนะไม่งั้นผิดนะครับโอเค phi is the angle between the normal vector which is this one. Okay, the dashed line here นะเขาสเก็ตรูปมาให้ด้วย the dashed line with respect to the magnetic field lines. Okay, this is the right angle, right? Here is the right angle, so you lose 60 degrees already to this one, so the remaining thing should be only 30 degrees right here, right? So phi is 30 degrees นะครับบอกว่าให้วาดรูปด้วยนะครับถ้าคุณคิดเลขอย่างเดียวสูตรอย่างเดียวคุณยังงงงวยแล้วคุณมีโอกาสผิดสูงนะครับผมถึงเน้นย้ำว่าวาดรูปแล้วก็ทำตัวเองให้เข้าใจกับบริบทนั้นๆนะครับ and the next thing is the area, right? AT doesn't change with time, so it's gonna remain the same, which is A, and it's circular coil, so we have to apply the basic formula from the primary school, pi r square, right? And pi r square is pi, right? And r is 4 centimeter, so you would have 4 centimeter. Okay, and then square, right? And what you get will be 16, right? But 16 pi, okay, times 10, let's just do negative 4, right? If you want to say in the SI scale, SI system, a square meter, and B, T, leave it like that. We don't know. Okay, they just say delta B per time per delta T is minus 0.2 Tesla per second จบ ข้อนี้นะก็เลิกแล้วครับ57ครับand ให้คุณเบรก20 นาทีครับ what else now we can apply or use this formula right delta phi b is the main important thing นะครับมันตอบไม่ได้นะว่า delta phi b มันจะเป็นยังไงครับมันขึ้นกับสถานการณ์โจทย์ครับ delta phi b per time is going to be phi b is so let's make conclusion to this one phi b is going to be a right and a cosine 30 degree and bt okay we would say the functional amounts at the end okay because all these two quantities are constants okay so delta phi b will be a cosine 30 degrees and delta b okay by delta t okay like this and we are gonna apply it to the Faraday's induction formula here epsilon is minus n and together with this quantity we have a cosine 30 degrees and delta b by delta t right in the number of turns they say 500 turns 500 turns oh no stupid 500 turns and oh no minus as well minus turns a is there right 16 pi 16 pi times 10 this is 2 negative 4 in square meter and yeah that's a and then cosine 30 is sorry ขออนุญาตจานนิดนึงครับsorry for that yeah cosine 30 is I don't know we can leave it square root 3 by 2 right and what else delta b by delta t right delta b by delta t is there what they have given is minus 0.2 Tesla per second right and you find that negative and negative will bring you to positive quantity right so you get I don't know put it into the calculator okay yeah um, 500 times 16 times pi times 1 e or 10 เขียนเต็มๆครับเดี๋ยวคุณไม่เข้าใจครับ minus 4 right minus 4ก็อะไรจำไม่ได้ and square root by 3 this one cosine 30 right cosine 30 which is pi by 6 right and times 0.2 okay we don't say negative at all because negative will cancel each other and get that positive thing and done done generate yes huh what happened syntax error What happened? I hope that it's all right. Okay, change it to E. It's no harm. 1E minus 4 times cosine pi by 6. What happened? ไม่เป็นไรเดี๋ยวคิดเครื่องเลขข้างนอกครับมันเกิดการเออร์เลอร์อะไรสักอย่างที่ไหนเครื่องนี้500 times 16 times pi times 1e minus 4 times cosine pi by 6 let's in times 0.2 we get 0.435 and 3118 unit for that is going to be volts, right? I hope that's correct. 343 yeah, all right, yeah, 4353118. Okay, exactly the same thing. Yeah, that's for today. We have consider the generation. ขออนุญาตสรุปพูดเป็นภาษาไทยดีกว่านะครับเดี๋ยวคนถามว่าสรุปเป็นภาษาไทยให้หน่อยนะครับก็วันนี้เราพิจารณากันเรื่องหาทิศทางกระแสนะครับที่เหนี่ยวนำกฎของฟาราเดย์นะครับผสมกับเลนมันจะต่อต้านในส่วนที่มันต่อต้านนะครับเพื่อให้หักล้างผสมกันฟาราเดย์ก็ได้เป็นทิศทางของกระแสนะครับแบบนี้ใช่ไหมเลื่อนขั้วแม่เหล็กขั้ว N เข้านะครับขั้วใต้เข้าหรือว่าขั้ว N ออกขั้วใต้ออกนะครับก็หาทิศทางว่ากันไปนะครับมันตอบไม่ได้ว่ามันทิศอะไรเพียงแต่ว่าคุณต้องรู้หลักว่ามันต้องดูฟลักเชนการเปลี่ยนแปลงของฟลักแล้วก็กดลวดพฤติกรรมกดลวดคือเป็นคนเฉื่อยนะครับต้องทำอะไรต่อต้านให้มันเป็นคนเดิมให้มันเป็นสถานะเดิมสภาวะเฉื่อยของเขาใช่ไหมครับเหมือนกับสภาวะที่1อันนี้ก็กระแสนะครับวิ่งตัดทำให้เกิดสนามแม่เหล็กวิ่งตัดหน้าขดลวดไปนะครับแล้วก็อันนี้ก็เหมือนกันก่อนอันนี้นะครับเขียนไหมจากหนังสือคนละเล่มนะครับจะเรียกว่าเลนส์ลอก็ได้แล้วก็ถ้าคุณไม่เลื่อนด้วยทางกายภาพนะจับของแล้วก็เลื่อนนะครับอันนี้คือคุณก่อให้เกิดฟลักเชนแบบทางไฟฟ้านะครับก็คือสับสวิตช์กับปิดสวิตช์ก็ทำให้เกิดฟลักซ์ของสนามแม่เหล็กเปลี่ยนแปลงได้ครับเพราะว่าตอนเปิดมันไม่มีสนามแม่เหล็กพอตอนปิดสวิตช์ลงเนี่ยก็คือมีกระแสไหลก็จะเกิดสนามแม่เหล็กนะครับแล้วก็ทำโจทย์กันไปนะครับใช้Faraday's law induction นะครับคราวที่แล้วขึ้น Faraday's law แต่ไม่ได้ประยุกต์ใช้นะครับก็สูตรก็อันนี้ขึ้นอันนี้เป็นหลักๆนะเท่ากับแรกนะครับแล้วค่อยมาว่ากันว่าโจทย์เป็นยังไงนะครับโดยใช้ไฟ bt bt at cosine phi t นะครับใช่ไหมขึ้นดูว่า3ปริมาณเนี่ยอันไหนเปลี่ยนแปลงตามเวลานะครับถ้ามันเปลี่ยนแปลงทั้ง3ปริมาณเราก็ต้องว่ากันไปตามนั้นโอเคไหมครับสภาวะ1สภาวะ2เป็นยังไงครับ final กับ initial นะครับโอเคไหมถ้าโดยส่วนใหญ่แล้วโจทย์ทั่วไประดับความยากปกติมันจะเปลี่ยนแปลงแค่ตัวเดียวครับนั่นคือจะเปลี่ยนส่วนใหญ่จะเปลี่ยนสนามแม่เหล็กหรือว่าจะเปลี่ยนขนาดพื้นที่หน้าตัดหรือว่าจะเปลี่ยนมุมอย่างเงี้ยก็คือเปลี่ยนมุมก็คือเรื่องเจเนเรเตอร์ละเพราะว่าขดลวดมีการหมุนโอเคไหมครับมุมเปลี่ยนนะครับแต่โดยส่วนใหญ่มันจะไม่มีการเปลี่ยนพื้นที่หน้าตัดครับมีข้อสุดท้ายของบทนี้จะเปลี่ยนที่ A โอเคไหมที่ผ่านมาจะเห็นว่าเปลี่ยนที่ B ต่อเวลาตลอดนะครับก็ได้ทำโจทย์มาให้คุณเห็นประสบการณ์การใช้สูตรนั้นครับผมทำสดให้คุณดูครับใช่ไหมไม่ย่างตามสไลด์นะครับเขียนสดๆให้คุณดูครับใช่ไหมแล้วก็หาทิศทางก็ตามนั้นนะครับใช้กฎของเลนส์นะครับใช้มือขวานะครับไม่มีอะไรนะครับแล้วก็ข้อสุดท้ายนะจะเป็นเปลี่ยนที่ตัวไป A นะครับเนี่ยข้อนี้ตัวนี้พิเศษนะครับก็ถือว่าเข้าขั้นว่าอาจจะเจอในข้อสอบเข้าที่โน่นที่นี่ได้เพราะระดับมันก็จะเห็นว่าโจทย์ทั้งหมดเนี่ยมันพื้นๆนะครับแค่พาทำใช้สูตรให้เป็นนะครับฝึกแทนเฉยๆแต่นี้ จะเริ่ม apply อันนี้เล่นที่ A นะครับเล่นที่ตัวแปร A นะตัวแปร A เปลี่ยนนะครับใช่ไหมพบกันครั้งหน้าแล้วผมเลยไป8 นาทีขออภัยด้วย if you have any question just let me know มีคำถามอื่นใดโปรดถามนะครับโปรดถามผมนะครับ if not we're gonna leave this section and I have to prepare for M605 alright นะครับก็เจ็บปวดนะครับตรวจกันบ้านคุณผิดกันตรงหาพื้นที่นะผมก็ไม่อยากตัดครับคนที่ถูกแล้วก็คงรักษาสภาพความดีคุณไปเรื่อยๆนะครับเก็บไหมตั้งใจทำมาครับ then see you tomorrow morning right Friday morning is tomorrow okay see you tomorrow bye bye ครับสวัสดีครับ